The last approach to amortized analysis that we're going to talk about is the potential method. Now, this is inspired by physics where, say, we have a ball, we have the ground, and we have a distance there that the ball is off the ground. The ball is drawn toward the ground and it has some potential energy that it can use up to get to the ground. We're going to be inspired by that in this approach. So we have C sub I, which is going to be the cost of the ith iteration of some function. And we're going to represent capital D sub I as the data structure after applying actually, instead of iteration, let's say ith operation. And so D sub I is the data structure after applying the ith operation. So whatever state the data structure is in is D sub I. And we're going to represent with phi D sub I, some function D sub I. That's going to be the potential of D sub I. And we'll now define the amortized cost to be C hat sub I, so that's the amortized cost. It's going to be the actual cost plus the change in potential. We're going to call that equation 17.2. Now, here we have the actual cost, as mentioned. And here we have the change in potential, right? So D sub I is the original state, is the new state, and D sub I minus 1 is the original state. So how much did the potential change as a result of this operation? And now we can get the total amortized cost over n operations. And that's going to be C sub I hat. That's going to be the sum over all n operations of using the definition of our amortized cost, C sub I plus phi D sub I minus phi D sub I minus 1. Now, these terms here are going to telescope, right? So in the summation, we're going to subtract off some and add some. They'll cancel out. And so we can simplify this to the sum over n of C sub I. And then outside of the summation, we're going to add on the potential at the final state minus the potential in the original state because of the telescoping and cancellations. Now, to have a legitimate amortized cost, we must have that the final potential is greater than or equal to the original potential. An easier thing we might do is to say that the potential will always increase. Okay, now let's do this. Let's show this using our stack. And we're going to let the potential function be the number of items in the stack. So very simple. Thus, the potential at any state d sub I is greater than or equal to the original state, if the original state is empty. Okay, so our potential function is the number of items in the stack, and we're also going to say that S is the number of items in the stack. So, for a push, what's going to happen? What is our change in potential? Now, recall, to find the amortized cost, right here, we need to find the change in potential from one operation to another operation. So for a push, what's the change in potential? Well, it's d sub I minus phi d sub I minus 1. And we decided that our potential is going to be the number of items in the stack. And so after we push, we have S plus 1 items. Subtract off, how many items did we have before? Well, we had S. And so then the change in potential is going to be 1. So what this means is that our amortized cost for that operation, since it's going to be the original cost plus the change in potential, which I'm just going to say delta phi, the actual cost of a push is 1 unit. And then the change in potential, which we computed here, is 1. So our amortized cost for a push is 2 units. What about for a multi-pop? Now let's define K prime to be the min of the stack size and the input into multi-pop. So if I want to pop K elements, I'm either going to pop K or I'm going to pop the total number of elements in the stack, whichever is smaller. And we're going to pop that, or call that K prime. So that's the actual number of items popped. Okay, so what is the change in potential for a multi-pop? Well, the new potential is K prime. And the new potential is the number of items in the stack, which is S minus K prime. And the old potential is the original number of items. So that's the change in potential, negative K prime. So what is our amortized cost of a multi-pop? Well, it's the actual cost minus the change in potential. And that's going to be equal to, so the actual cost is K prime. And the change in potential, as we saw here, is negative K prime. I'm sorry, it's Ci plus the change in potential. Ki plus negative K prime. So the amortized cost of a multi-pop is 0. And we could do a similar analysis of pop. And so the amortized cost of all 3 operations is constant, 2 or 0. Therefore, n operations is going to cost linear time. Therefore, we have the amortized cost here, which is constant, and over n operations it's going to be linear. That is the potential method.